So today I'm going to talk about some of the relation between the normal pointer operator, let's say the adjoint of the double layer operator on leftist square with what we call undefined Laplacian. And the undefined Laplacian, in fact, will be modeled like a linear operator with transmission condition along hypersurface. So in fact, this is an ongoing, this is the first part of an ongoing project with Contact2024 who is in Oldenburg.
Yes. Spinge examining, spinge examining, filato, spinge examining. That's the go.
Maybe you need to put the mouse on the PDF.
Please don't touch this because this causes the table. No, questo cavo è pericoloso. Vabbè. Forse dobbiamo chiamare estremista. Vai, muova. Ah, ecco.
Ok, perfetto.
Bisogna farlo scalo.
Okay, so anyway, so in the following, so we first start by motivating the problem from a physical point of view and from, I say, about the difficulty from a mathematical point of view. Then I will just recall what is known, the result that we know in smooth case and some partial result in the Lipschitz case. Then I will state our main result and some application. And in the end, I will give some main idea of the proof and state some questions for we are interested. Okay, so in fact, the problem comes from different, like for example, from the mathematical theory of electromagnetic, of negative index material. So what is this? In fact, so we assume that we have like a domain omega of the protein, but this domain is split by a contrast or hypersurface sigma, where here we have a material which say has a positive electric permittivity and here negative electric permittivity. So those are two different materials. Okay, so and in fact the problem is for people who are doing numerics in this subject. In fact, the question is, we ask for solvability of the following problem. So we ask the question whether there exists a function f, which is in H1, that satisfies this equation with f vanishing on the boundary of omega, and here g is just a source term, let's say in L2 or in h minus 1, h minus 1. So because of this sign changing of this function h that we have here, in fact, we will see that this is actually a transmission problem along this hypersurface sigma, okay, because of this change, of course. And the question that we ask, is this problem well posed? And if it is not, why? Those are obvious question. So let's see what we can do with the Lax diagram. So if we assume, for instance, that the function is positive and on the whole domain omega, so then you define this quadratic this bilinear form, and you see immediately that it is bounded from below, and therefore Lax diagram says that the problem that I stated before is well posed. However, if the function changes the sign, then obviously you cannot use like spectrum. So then one needs, I mean, different techniques to solve the question. But anyway, since I'm doing spectral theory, so what we do is in fact we ask a more general question. So we are interested then on studying this operator minus d h grad f with assuming that we have this Dirichlet boundary condition. So and then the question that I'm asking before, in fact, is just whether zero is in fact in the spectrum or not. So if zero is in the resultant of this operator defined in certain domain, then we just invert and we get a solution. And then we see if it is in H1 or not. Okay, anyway, so now before defining rigorously the operator, let me just recall you some well-known facts about Dirichlet Laplacian on Lipschitz domain. So in the following, let us assume that we have a bounded domain U with Lipschitz boundary. Here I'm always assuming that the dimension is higher or equal to 2. Then denote by U unit normal to this domain. No? So and then I consider this Sobolev spaces where I'm taking F in HS, and I assume that in the distribution sense, the Laplacian of F is in L2, and this is for S in the real line. So we equip this this Banach space with this norm, and in fact it is the Hilbert space. So then, what is known, in fact, for any S in this range, the Dirichlet trace and the Neumann trace are in fact well defined and bounded. Of course, for S bigger or equal to bigger than 1/2 of this, then everything is well defined. It is well known. But remember that in fact, if we do not assume that we have this condition that Laplacian, we just take, for example, H1/2, then if we take the trace, then we are not sure. In fact, there are good examples where, in fact, in the end, you don't get the function which is the L2 of the boundary. So having the Laplacian in L2 of U guaranteed, for example, that for this for the super regularity 1/2, we end up actually in L2. And of course, I mean, we can extend this range until 0, but unfortunately, I mean, the Sobolev space of order greater than 1 are not defined in unique and varying way. So this kind of result, you can find them in Bernd and the whole. So, and then, in fact, the Dirichlet Laplacian defined on U, that is in this domain, then it becomes a separate joint operator. And in fact, H3/2 is the good Sobolev regularity for the Dirichlet Laplacian. Okay, so up to now, from the motivation, we saw that we are looking for fraction in H1. So this is more or less for people doing numerics. So this is the motivation for the variational techniques. So we have H1 as Sobolev regularity, and we have here H3/2 as Sobolev regularity. So I will be interested on studying spectral property and superjointness of this undefined Laplacian for the regularity S in between 1 and 3/2. Okay. All right. So that's now that I'm going to simplify somehow the problem. So in the following, in the rest of the whole talks, omega will be again bounded Lipschitz domain, and then I'm denoting by omega plus and omega minus these subdomains.
Excuse me, just a question.
Yeah.
Submit the previous slide.
Yeah.
The domain of the Laplacian here is just an equivalent relation of H2 or not?
No, this is not the
H2 intersected with the H10.
No.
Why not? Because in the case the boundary is C2, this should be the previous extension.
Yes.
So
So you intersect H2 with H1 half.
H1 0, yes. H2
Yeah,
is so it's much regular. So it's equivalent or not?
Yeah, in fact, if you define, of course, I mean, the definition applies in H1 0. So in fact, this is the joint and this unit, you have uniqueness. By uniqueness, I mean you have this sort of regularity. So in fact, behind there is elliptic regularity. So if you start with H1 0, then you can prove in fact that your function actually has this sort of regularity, and it is sharp. So for the Lipschitz domain.
So okay, it's a pretty if I'm regular, then I can see that I have also H2 regularity.
Yeah, you're right. Yeah.
Okay, so I go by
Exactly. Yeah.
okay.
Thank you very much. Yeah, I mean, for as I said, is that for Lipschitz domain, this is that the best that you can get.
Okay.
Okay, so as then I'm considering again the same situation, and I'm denoted by partial omega exterior boundary. Then I will simplify my function h that I said in the beginning by saying the following. So I'm taking a parameter mu, which is real, and the function now h will assign for x in omega plus 1 and mu in omega minus. And also, I'm going to use this kind of notification for omega. So we will have that sum. That is, I mean, for a function here in omega. So we'll have a couple of functions, plus and minus, given just by the restriction. And I'm using also this notation for the direct sum of those spaces. Then, in fact, then we have now the definition of our operator that I'm denoting A sub S. S is for the super regularity. So here, the action of my operator is as follows. So we have just minus Laplacian in omega plus, then minus mu Laplacian in omega minus. And then we have our parameter mu. Okay. Then the domain, as I said, I mean, we assume that we have Dirichlet in the exterior. Okay, we have the continuity of the Dirichlet traces along the interface, and now the transmission condition is this one. Okay, so what do we have here? We have our parameter. Here we have the Neumann trace that comes from inside, plus Neumann trace that comes from omega plus. So we assume that this vanish on sigma. And so with those boundary condition or transmission condition, so we can show in fact that what we have here is a symmetric operator. Okay. All right. So now let me just give some well-known results. So in fact, this problem, I mean, people start working on this in the beginning of 90s, something like this. And start with Bonnie Benhallal from Paris and Rennes, like Costabel, for example. So there are many people who are involved in this subject. But so what is known actually? So we start for smooth domain. So let us assume that my omega. So I will pick the picture here. So this is omega. This is omega minus, omega plus. So the normal is mu here. Okay. So if you assume that omega plus is city smooth, then it was shown that if the parameter mu is different from -1, then A1 is center-joint with compact resolver. A1 that is the one with H1 superregularity. Okay? But in fact, due to this regularization property, in fact, we have A1, which is equal to A2. Okay, so we start with A1, then you show that you have regularity. So this was done by Bonnie Benhallal, Dodge, Amdani, and also Dodge and Dixie. So and
is -1 center over GFTs.
every come on this, yeah. So actually, mu equal -1 is what we call critical case, and we will see why it is called like that. All right, so okay, so now what happens, for example, if we assume that we are in 2D, So I'm given sigma now will be just a smooth curve that has one single corner with angle, let's say omega different than b, it's not flat. In fact, that Bolivia, Dodge, and then they showed that the A1 is separate joint if and only if the parameter mu is not inside this interval. We depend on the angle of omega. Okay? And so what is the difference between this result and that one? What we say that here, if we are smooth, so we have like, let's say, a problem for -1 when we are smooth. And then if we just assume that we have just one corner, we are smooth outside, then in fact we have an interval, let's say around -1, where outside of this interval, in fact, we are separate joint. So A1 is separate joint. But inside, except for the point -1, we will see why it is not. So in fact, if the mu is inside the interior of this interval and it is not equal to -1, then one can show that A1 is closed with the efficiency, and this is 1, okay? And for the closure, so here you do it by hand, in fact. So you can construct, you can add some element for the domain so that you get a separate joint operator. But by doing this, in fact, you will not get. So when you add this element, in fact, you lose solar regularity. So, and in fact, we will see it in this theorem in the case of smooth domain. So now, if we assume that omega plus, again, that means that this hypersurface sigma is smooth and also the exterior is smooth. So in this critical case, if you assume that you start that with H2, solar regularity, then in fact it was shown by Casciopote and Pankrashkin and Pozelikano that in this case your operator is essentially separate joint. I mean the closure is separate joint. Okay, but then we have some difference between the two-dimensional case and higher dimensional case. So in 2D, what happens is that the closure is given by A0, is the maximal, the operator of the maximal domain. And 0 is in the essential spectrum. The essential spectrum is exactly 0. You have just one point. But if you are in higher dimension, then, and if you add some extra assumption, for example, if you suppose that the principal curvature of the hypersurface sigma are all strictly positive or all strictly negative, in particular if sigma is just strictly convex, then in this case, the closure of A2 is A1, which means that you have some regularity, and this will imply that you have a compact resultant, and in particular, you have just a point spectrum. But if you suppose that sigma, this hypersurface contains a flat part with positive measure, then you can show that 0 is in the essential spectrum. And because of this, you don't have any super regularity, and therefore you cannot solve the problem that I stated before. So for this situation, the problem B that I stated in the first slide, in fact, we don't have a solution in H1. We don't have the impact solution in HS. So as I said, this was shown in this paper. And in fact, there are some analogies with the Dirac operators with singular interaction. So if you take the Dirac operator, let's say in R2, and you put the delta distribution on a curve, or in R3, and you put the delta distribution on the compact surface, namely this kind of potential, I showed with Pankrashkin that in fact you may create essential spectrum in the gap. Let's say for massive Dirac operator with mass m, so usually the essential spectrum of the Dirac operator is just -n. So this is the essential spectrum, is two infinite intervals, But in this case, when the parameter, in fact, lambda is equal to plus or minus 2, then in fact, depending on the dimension, for example, in dimension 1, you have again just one, you add just 0 in the essential spectrum, but in dimension, in higher than in 3D, you might have, I mean, an interval inside this gap. So you add, and you can actually fill all the gap, and then the essential spectrum will be a whole regular line. And we see here the geometry. So I will come back to this in the end. So anyway, now to state our main result, let me just recall again some notation. So in the following, C will be just the usual fundamental solution of Laplacian in Rn, is given by this. Then I define the usual boundary single layer operator in this way. Then there we have second interesting guy in this talk, which is Neumann Poincaré operator. So this is this operator that I define from L2 to L2 in this way. Then it is known that in fact, so this should be H. So it is known that the single layer is bounded from HS to HS plus 1 for any S in this range, and this Neumann Poincaré operator is well defined on this domain. So let me just recall you that this property for the single layer. So imagine that you consider in the 2D case the single layer of this boundary single layer operator. So and if you define let's T sigma just the x is sigma. So in fact, if let's say if sigma is C1, then in fact we can always there is always we can always find T positive such that in fact S over T0 sigma is not injected. Simple computation, one can do it. And in fact, for Lipschitz case, this means that there are some situations where, in fact, the single layer defined in this way is not bijective. This condition will change later. Okay, so again, another notation before the main result. So in the following, for a bounded linear operator T in a balanced space, let's say H, I define this essential spectrum and the radius and of this essential spectrum is ohms. So the essential spectrum is just a set of complex number where T minus Z is not a zero index freedom operator. Okay, so then our main theorem is as follows. So assume that sigma is Lipschitz, and we fix a super regularity S. Then for mu in this range, we suppose also this condition. We assume that this parameter is not in the essential spectrum of the Neumann Poincaré operator, where the Neumann Poincaré operator we see as a bounded operator from HS minus 32 to HS minus 32. And we suppose, in addition, because of this, that the single layer is freedom with index 0. Then in this situation, the conclusion is as follows. In fact, AS except a joint will compact result. And this, in particular, these conditions is satisfied if we suppose that in this case, when the modulus of this number is greater than the radius of the essential spectrum. Okay, so in fact, this, as I said, this condition we need it only for dimension 2 because of the fact that the single layer might have a non-trivial kernel, and therefore, I mean, it will not be 3-to-1 between HS minus 3 half HS or minus 1. Okay, so this is somehow abstract. So let's come now to the application. So the first application which is obvious, of course. So for positive parameters, so that means now the sign-defined case. So in fact, A with super regularity 3/2 is separate joint, and this is without any assumption, any expansion on sigma. And in fact, again, we can show that A 3/2 is equal to A1. Now, the second, say trivial again, application is the case when sigma is VMO surface. So what is VMO? So VMO is just a space of vanishing of a function with vanishing mean oscillation. And so, well, I mean, we can say that VMO is close just to C1. It's very close to C1, but it is not C1. But in fact, VMO are those hyper surface do not have corners. You can see it like this. So in this case, in fact, again, we have separate jointness for any mu in R without, of course, this critical case -1. So in fact, this situation, because this just follows because in this case, this Neumann Pointer operator is compact. So, and the condition is fulfilled for any mu in this. So, well, I mean, up to now, we don't have anything for corners domain. So you should be, I mean, most important question somehow. Yeah, well, I mean, in fact, and we up to now, I mean, we just got somehow a range which can change that positive views in some sense. So, what can we say about negative view? So, in fact, if we just I mean, take R, which is the radius of essential spectrum, so in fact, if we suppose that this is strictly smaller than 1/2, then we can show that this relation is bigger than R, that is, this condition is satisfied if and only if mu is not in this kind of critical interval. So under this assumption, then our operator AS will be self-adjoint for mu which are not in Dishman. So just as a remark, in fact, let's say in L2, for example, or in H1/2. So the question whether the radius of the essential spectrum is strictly smaller than 1/2, or the radius of the spectrum is strictly smaller than 1/2. This is, I mean, a very hard question, and a problem by Kenning in '94, and still now, I mean, we don't know too much about how to solve it. This is very hard problem. Okay. So, but still we have some partial result. So, and it goes as follows. Now, I'm going to restrict myself to this case where we are in 2D. Sigma is curvilinear polygon with n interior angle that I'm denoted by omega g. And I will take the angle omega, which is sharp in the following sense. In this sense, then under this condition, so we have the operator with some regularity 3/2 is separate joint for all mu different than 0 with mu which is not in this critical interval, and A omega is given by this constant. Then for the H1 formal regularity, we have the self-adjointness for mu which is not in this interval. So obviously, I mean, we have this kind of inclusion. So 3/2 is included in A1. So what we say here, in fact, so let's say that this is in fact A1. Then in fact A 3/2 is something bigger. Okay. And so this is so we have something here. So in fact, inside this thing here, the operator A3 is in fact essentially a software joint, and the closure in fact is A1. Okay. All right. So and in fact, this interval here is exactly the same as the one in Benhallal, Dodge, Lambda. So let me have it here. In fact, this is the same. Okay, in fact, this is exactly the same. What we are saying here is that, and thanks to this, what we are saying that in fact we are self-adjoint if and only if the normal pointer operator minus this constant is trade-off with index 0. Okay, so this is the relation between this undefined Laplacian and the normal pointer operator. Okay, so the last application in 3D. Now, so we assume that we can obtain our sigma by just a revolution of C5, a smooth curve, and we suppose that our sigma is just smooth except at one conical point where we have a singularity with angle alpha in this range. Then we have two things here. So if we suppose that in fact this angle alpha is in between 0 and pi over 2, then A1 is self-adjoint with compact resolvent for mu greater than -1. And if alpha is in this range, then we have the other sense. Mu is smaller than -1. And in fact, what happens here under this assumption of our hypersurface, in fact, the Newman Poincaré operator has a time. Okay, so and with this you can get two strange depending on the angle how you get the side. Okay, so you can find this in this paper. Okay, so let me just say something about the idea of the proof. So I will do just the case S is equal to 3/2. So let omega plus minus be the direction Laplacian, and I set B to be the direct sum. So in this way, B is just a self-adjoint operator, which has just a point spectrum that accommodate depending on sign of mu to plus infinity or plus infinity and minus infinity. So and then for Z in outside of the real axis, we define the Poisson operator associated to this problem. So our Poisson operator it solve this this problem. Then, in fact, the adjoint of this Poisson operator is given exactly by this formula. And once you have, of course, a Poisson operator, then you can define Dirichlet-Neumann maps for the domain omega plus and omega minus. So for omega minus, we just take the Dirichlet-Neumann map, the usual one. But for the exterior, you add this condition. In fact, you project 0 on this on the exterior boundary, and then the Dirichlet-Neumann you project it again on the hypersurface sigma. So you have this kind of matrix block operator. And then we consider this those operators theta and mz in L2 defined on the domain H1, which are given just by this Dirichlet-Neumann operator. So what do we have here? So we have theta which do not depend on z, and then m which depend on z. This given just by the difference between the Dirichlet-Neumanns with z and without z. So I write it like in this way. Maybe some people here are familiar with this boundary triple theory. So this is in fact the relation that we have in the boundary in the transmission condition, and this is the Wave function, and here and the P Poisson operator is in fact the gamma function. Okay, so for this super regularity, one can actually use the boundary triple, but for S less than V half, and in fact, we could not, I mean, in fact, use it, we didn't manage, I mean, to find the boundary triple for this situation. So, in fact, somehow we follow this boundary triple theory, but we prove things just by hand. So what we prove is the following. In fact, if you take Z, which is outside of the point spectrum of this Dirichlet operator, then you have this Birman-Finger principle. That is the kernel of our operator related to the kernel of theta minus mz. And in particular, because our operator is symmetric, so you get for free that theta minus mz is injected for all z. So, and second point is this kind of resultant formula. So it says what it says. So the important thing that here is that when you pick, let's say, z outside of real axis, your theta here, theta minus mz is injected. So if one manages actually to show that this guy is invertible, meaning that it is surjective, so we need surjectivity, then this defines the resultant formula. So, and with this, so this shows that in fact the kernel is empty for non-real z, and with this you will show that the range is L2 of the whole space. And this shows that your operator is separate. So the main point, in fact, is to show that in fact theta minus mz is surjective. This is the main problem. So and for this, at this point, I mean the Newman-Poincaré operator games. In fact, if we have the following, so for mu in this range, if you suppose that this is freedom of index n in z, and the single layer is freedom with index 0, then in this situation, one can prove that theta minus mz is freedom with index n. And the dimension of the orthogonal of the range is exactly n. So in particular, under our assumption in the main theorem, that is m is equal to 0, theta minus mz is of course surjective. And this will show the previous result. So at this point, so we see, in fact, one can write, so in fact, theta minus mc, one can write it like constant k prime u plus 1 over 2 u minus 1. Then you have some freedom operator plus compact operator. Okay, so there, I mean, there we see how freedomness of this operator is related to the freedomness of this operator. So the result that I showed you in the application is exactly the situation where we have some information about the essential spectrum of Newman-Poincaré operator. Okay, so I think I have 2 or 3 minutes. Let's see. Yeah, well, I mean, I will finish just with the slides. So up to now, as I said, this is in fact the first part of an ongoing project, and we didn't manage, in fact, to go until what we want somehow. So in fact, we believe somehow that when suppose that this operator is freedom of index n, then actually one can show that AS is closed, symmetric of course, with the deficiency indices m and n. And this is because of this. I mean, somehow, because the orthogonal of the range is of dimension n. And since you see somehow, so the idea, let's say, so the idea somehow is just to add the element that are missing in this kind of resultant formula, so that we can define a resultant for let's say for the closure of our operator. Okay, so we think that this must be done, and also I mean one of course, I mean, the main question here is that what can we say about the essential spectrum of this Newman Pointer operator in loose space HS in this range? Sure, I mean, just I mean, consider this case, but also one can goes beyond those range. I mean, let's say one could consider, I mean, 0 and 3.5, but apparently, I mean, one should, I mean, somehow rebuild this theory about the trace operators for this whole range. But we think that this is possible. And now, so actually, in fact, we are also working on what happens in smooth case. So as we have seen, in fact, in dimension 2, we have seen that, in fact, we have just one single point in the sensor spectrum, which is 0. Now, in fact, a natural question would be, so in this case, could we, I mean, somehow describe how, I mean, we have an accumulation near this point 0. So in which sense, depending how you accumulate. So, and the second question, because of somehow what we did with Pankratkin for the Dirac operator. So we are looking in some sense that for some geometric structure, where in fact we could actually have the whole real line or create an interval of the essential spectrum. And but I mean, compared to Dirac operator, it seems that this problem is more involved and more difficult because actually we immediately saw how the geometric challenge appears in this case. And I think this is my last slide. And thank you.
For your presentation.
We can give it.
Okay. All right. So, first of all, thank you, and time for questions or comments. Or you want to answer, please.
So, some results
You mean for this Newman Poincaré? Yeah, well, in fact, we have somehow we have a result, but we do not have bounds for the essential spectrum. So they are not explicit.
You just find like how geometry would be with like the opening angle would be.
Yes, yeah. I mean, it involves some basic function, but I mean, you don't have something which you can compute and estimate. There are some results, but you could not even apply them.
But for example, based on that paper of yours that you mentioned in the previous slides, at least if you have spheres. Okay, yeah.
Maybe just push any.
Yeah, yeah.
Based on this one last, if I remember it correctly.
Yes.
If you have spheres,
Then you get all.
then you get
spheres.
spheres. So
Only
we
one
have-
was, yeah.
So I will follow with the question. So nothing can be said on, for example, the concentration of the spectrum. Especially at one point.
Yeah, still we don't know actually.
That is a phenomenon that depends.
In fact, now in the case of the sphere, in fact, for the Dirac operator,
Okay.
in fact, it is an eigenvalue with
Yes.
infinite multiplicity. Yeah. And here also, I mean, for this Laplacian, you have again, because I mean, it's strictly convenient, so, and in fact, you can have infinite, again, in this situation. So for the sphere, for Laplacian, we know that we don't have an essential spectrum. See, so.
May I also ask, so unfortunately, I mean, to my personal taste, if you characterize the operator with a triple, it obfuscates the mechanism why. Could you elaborate on the mechanism why? Okay, you have a triplet. So if you have a triplet, you're happy because your operator is set for jointed. They have a varying formula, which is number one, and I think you're happy. But I can't grasp the mechanism why for certain moves, for certain negative moves, of course, you finally have these adjuncts, and instead you don't have the existence of these triplets for other moves. I mean,
Yeah, well, in fact, this is the
phenomenon behind.
well, I mean, for S,
Yeah, fix that.
for this S, but you have a quadriband boundary. This is important. It's different.
Yes, yes.
So in fact, you don't have any this.
Yes, they exist a lot of these
Yeah, so you could have I mean, cut the boundary triple, and then you don't get any separate. So I mean, the missing point here in this program is
So that's not a triplet.
so the triple. I mean, the boundary triple here in this case would be L2 as a space,
Yes.
and say the gamma zero. You just take the trace on your hypersurface. Then let's say the gamma one would be just I mean we can see it directly here. In fact, the gamma one would be, let's say here you take so the gamma one applied to a certain f would be just minus the Dirichlet that came from exterior, then minus the or plus mu the Dirichlet the Newman trace. Sorry, amounts. Minus, then you have here theta applied to gamma zero of your f, and the gamma zero, as I said, gamma zero of f is just the trace, the Dirichlet trace of f on the hypersurface sigma. Okay, so I mean, somehow, I mean, if you want to apply really, I mean, the quasi-boundary triple, or so one could consider theta as an operator, not a bounded operator from H1 to L2, but I mean, as a certain joint operator. So this is what we are treating in this program.
So are there studies about this kind of problems also from boundary domains? So maybe you have sigma and you have Rn minus omega, and there is a interface sigma.
I don't think it's done, but I mean it's the thing is that this exterior boundary, I mean, don't play any role. So you can of course I mean consider omega plus just exterior domain of the domain.
So doesn't play any role.
Yeah, it does not play any role. But I mean just for the application and motivation. In fact, this is because in fact in 2D, for example, the operator that we are studying, you can view it like what you start with the Maxwell equation. So in Maxwell you have the electric and magnetic permeability. So if you neglect, there is certain materials where you can neglect this electromagnetic magnetic permeability. So and you end up with minus d grad equal to something. Okay, so if you consider certain, let's say, this you can view it as a waveguide, okay? And this is like a cross section. So with the Hodge decomposition, in fact, you can reduce from 3D to 2D. And in fact, what you see here is just the cross section of this sort of waveguide.
Let me continue the argument for unbounded. Actually, assume that sigma is proper. And we have this exterior boundary. It is very interesting that such problems with real equal one, similar effect probably you can find if you consider omega minus as obstacle black box. Yes, if you put Roman boundary conditions to the boundary, because they also have parameter mu. Yes, again, you shall have similar effects. But then there is very interesting observation since many years, what will be the fact what will happen if you send a wave towards your obstacle. And there is very nice phenomenon, disappearing solutions. So you have solutions with initial data non-zero, and then mu is exactly this minus one, disappears. And this is very interesting, we're starting exactly with Maxwell.
Yeah, in fact, there are exactly the same phenomena for this kind of model. So you have this way to disappear, and in fact, it disappears namely near the corners. You can see it, and you are creating something. Let's say that this is the corner. So you are creating like a black wall here somehow.
Be careful, when that corner, this what we put as a picture, this model that, imagine that this aircraft jet,
Yes.
and you want to hide the object. So these corners are very terrible. You know how ones are very smooth. So these appearance solutions are not caused by this, by limit or minus one. This is the reason.
Yeah, what I'm saying also, in fact, even for, let's say, because when we are not smooth, that when we have this corner, so we have an interval. Okay, so, and for this interval, so outside, I mean, beside this point, which is, we know that it is critical even for smooth. So what happens is that, except at this point, you have kind of absorption near this corner because of this deficiency and this.
If you can show me after this.
Yeah, we can do that.
Called disappearing solution for corners, I shall take it.
Yeah.
Thank you very much.
So what about if omega minus is about 2? So maybe, I don't know, 2, so you have a 2 and you divide into 12 days. That interface.
Yeah.
Is it more?
I think things should be done in this situation, but I mean, our operators still, I mean, will define and so on. But yeah, one should be very careful on the regularity. And let's say for smooth, that's C1, for example, you assume that I mean, just the hypersurface sigma is now just a graph of C1 function, then in this equation, you can show that you are separate joint and all those things. But again, you will have this parameter -1, which is critical. But yeah, I think nothing is done with something